All right, well, we're going to jump right into our kind of first foray into organic chemistry. Chapter one had a little bit, or part one had some, but it was a lot of review from general chemistry. And now we're going to kind of jump into going into like functional groups. And I haven't talked much about those yet, but functional groups are how we classify compounds, how we put organic compounds into families. And the first of these functional groups that we're going to start off with are known as alkanes. And this will kind of kick off a series of chapters where we're going to focus just on hydrocarbons. Hydrocarbons are compounds that contain only hydrogen and carbon. And within that, there's a lot of different divisions of hydrocarbons that we'll spend some time on each division. But we kind of group them into two major categories and then break them down even farther from that. But the two categories that we look into are saturated versus unsaturated. Saturated hydrocarbons only have carbon-carbon single bonds. So all the carbon bonds in saturated hydrocarbons are single bonds. And then unsaturated, these hydrocarbons have pi bonds in them. And in fact, you probably have already used these terms without even knowing what they mean as they apply to like compounds like fats. You've probably heard the terms saturated fats or unsaturated fats. And that literally the difference between them is that in saturated fats, there are only carbon-carbon single bonds, and unsaturated fats have pi bonds in them. And that's really what defines those two. So what we're going to go into first is how we name these compounds. Now, this is one of our first like super important foundational organic chemistry skills. What you're going to find is I'm going to spend a lot of time on nomenclature in this chapter. And then as we look at different functional groups, it really becomes less and less because all of those rules we learn in this chapter are going to apply to subsequent functional groups. So it's very important that you master nomenclature now. Otherwise, it's going to continue to haunt you all throughout OChem and even into next semester. Um, so the nomenclature has become standardized over the years. In the beginning, like in the early 19th century, basically, if you discovered an organic compound, you named it however you wanted to name it. And you can kind of see these are some of the common names for some compounds you probably have heard of. Um, and then near the end of that 19th century, an organization called IUPAC, or the International Union of Pure and Applied Chemistry. This was formed, and part of this organization was to standardize the nomenclature of organic compounds. And so these IUPAC rules led to what we call systematic names. Now, you might hear me use those terms interchangeably. So I might say, like, give the IUPAC name for this compound or give the systematic name. It means the same thing. You're going to be using this series of rules that we're going through. So rule number one, and this will apply again, all these rules will apply to subsequent chapters that we cover. The first thing is find the longest continuous chain of carbons. Now, that can be super simple, or it could be a little bit more complex depending on how large the compound is. And don't lock yourself in reading left to right or right to left. You might need to go up or down. So here's kind of an example. This is like an extreme example of this. So here's like the skeleton formula for a very large organic compound. Now, the first goal in no in or first task, I should say, is finding the longest continuous chain of carbons. Now, if I were just to go left to right on this, like one, two, three, four, five, six, okay, I could do that, or um, I could go like this: one, two, three, four, 5, 6, 7. Now that's a little bit longer. What if, though, I switched to this? 1, 2, 3, 4, 5, 6, 7, 8, 9. Now I have 9 carbons. And notice I didn't necessarily go left to right or right to left. I just found the longest continuous chain of carbons in a row. And so this would be what I call my parent chain. And that forms the basis of the name. Now, what do I name a chain of 9 carbons? That's where this table comes into play. And I want you to memorize this table, not just to give you something to do, but because these are the most common parent chains, especially 1 through 10, that you're going to see in organic chemistry. And so if something has 1 carbon in it, and it's just a hydrocarbon, we call that methane. Or if it has 2 carbons, we call it ethane, and so on and so forth. What I want you to get out of this is a trend. First of all, I want you to look at the prefix here, the prefix meth. Anytime you see a compound, the IUPAC name, or let me back up, sorry. Anytime you see a compound that has 1 carbon in it, whether it's an alkane, or maybe when we start talking about alcohols or aldehydes or anything like that, if it has 1 carbon in it, the beginning of its name will be meth. And then the end of its name here, that ANE, tells you the functional group. That tells you it's an alkane. So it's a saturated hydrocarbon. The ending for that name will be different for a different functional group. So like, for example, an alcohol will have an OL ending, or an aldehyde will have an AL ending. I don't expect you to know those now. We'll go over them. I'm just kind of giving an example of showing you how that suffix changes based off of the type of compound it is. So any organic compound that has 2 carbons in it will have a prefix of eth. 3 will have a prefix of prop, and so on and so forth. So I highly recommend committing these to memory so that you know those prefixes. So if we were going to name the parent chain for this compound, since it has 9, its parent name would be nonane. Now we will talk about what we deal with those other ones. Notice there's a bunch of carbons that I did not highlight. We'll get to that next, but that's the first step in nomenclature. The second step is to number that parent chain, and you start at the end nearest a substituent. Now, what is a substituent? Those are those carbons that are not part of the parent chain. All right, for example, let's look at this structure down here at the bottom. Now we're going to find the parent chain, which is going to be this chain of carbons here. That forms a parent chain of 1, 2, 3, 4, 5, 6, 7, 8, 9 carbons, versus the other one would only be 8. Now I got this guy hanging off the end, those 2 carbons, not hanging, sorry, hanging off the kind of the middle of the chain there. All right, I'll talk about naming those in a second, but when I number this, I'm going to number starting here. 1, 2, 3, 4, 5, 6, 7, 8, 9. Because that gives the substituent encountered first the lowest possible number. I'm not going to go the other way, like 1, 2, 3, 4, 5, 6. Because it puts that carbon group, that 2 carbon group there, it gives it a number 6. And the rule of thumb is we want the lowest number for that first substituent. So now that I've located that substituent, I'm going to name it. The foundation of the name is based off of these prefixes. So I have a 2 carbon group here. So if I look at my table, that 2 carbon group, I'm using a prefix of eth. And when a carbon group is a substituent, I change the ending to YL. That's standard across the board for all substituents. The end of that name changes to YL. So as I put here in the notes, a 1 carbon group would be called methyl or methyl. with that YL ending. Now, if all I have is one substituent, I'm kind of ready to start forming the name. At the beginning of the name, I'm going to put where the substituent is at, so a number 4, and then I'm going to put a dash. A little bit of a housekeeping thing here. You always separate a number from a letter with a dash. So I say for ethyl, and then I put my parent name. 9 carbons is nonane. Typically, there's no spaces. There'll be some exceptions to that, but it's just like kind of think like one big run-on sentence. So these names can get very long, but you don't put any spaces in there. And as I said before, you separate a letter, a number from a letter with a dash. Okay, so that's how we treat the compound with one substituent. Pretty simple. Make sure the substituent gets the lowest number. Now, what happens if we have more than one substituent? Well, every substituent gets its own number. All right, but we're going to start all the way back at the beginning. So let's look at this example down here. I'm going to find the longest chain of continuous carbons. Now, that means for this one, I can go like this, or I can go like this. I get the same parent chain with the same substituent either way. So it doesn't matter which of those pathways you choose. I'll just choose this one because you get the same result either way. Now let's go back to our the second rule. I'm going to number this parent chain. So the substituent encountered first gets the lower number. That means I can go this way, 1, 2, and those bromines are on 3. Or I go this way, 1, 2. Well, the rule says the substituent encountered first gets the lower number. So that's how I'm going to number it. So 1, 2, 3, 4, 5, 6. Okay. Now let's identify our substituents. On number 2 here, I got a 1 carbon group. So go back to your table, look up what 1 carbon is. That's a prefix of meth. So I call that a methyl group. Now I got these other groups here on 4. We got bromines there. You'll kind of pick this up along the way, but with the halogens, we kind of take off the ending. And so we call these a bromo. Those are bromo groups. Now notice I got 2 of them here. Anytime you have the same substituent multiple times, we're going to use numerical prefixes like this, like di, tri, and tetra. So the beginning of this name, I'm just going to make this a lowercase b. So we would refer to that as dibromo. All right, so now I'm ready to start forming the name. The question is do I put bromine first in the name or methyl in the name, or does it really matter? The answer is yes, it does matter. We're going to alphabetize the substituents. That's the order they come in the name. The numbers might be in order, they might not. We don't care. All right, we alphabetize them and put them in that order in the name. But here's what I want you to do. I want you to circle, highlight, star this phrase right here. We don't use numerical prefixes to alphabetize. So dibromo counts as bromo when we alphabetize. If it were tribromo, that doesn't mean we go down to T in the alphabet. The numerical prefixes are not counted in alphabetizing. So bromine comes first in the name. So there's 2 bromines on number 4. Each one gets a number. So I don't just say 4, I say 4 dibromo. Now here's another housekeeping thing. Notice I used a dash here to separate a number from a letter. I use commas to separate 2 numbers. So that's why I have 4 dibromo. And again, I want to emphasize, even though both of them are on the same carbon, each of them gets their own number. Because if I were to just say 4 dibromo, it's really vague about where that second bromine is. Well, is it on number two? Is it on number three or four? Or where is it? So that's why I emphasize putting two fours there to indicate that both of them are on the number four carbon. Then I'm going to indicate the methyl group. It comes second in the name because it's alphabetized. Its alphabetical priority is lower than that of B, the bromo. And then I put the parent name at the end. 6 carbons is hexane. Now, what we're going to kind of focus on is some special cases. This may or may not always occur, but it does come up. So what happens if I can number a parent chain in two different directions and they're not the same? So here's what I mean by this. Let's say um, I number this here like this. 1, 2, 3, 4, 5, 6, 7. Okay, I number it that way. But what I could also get that same numbering, I can get 7 by doing it this way. 1, 2, 3, 4, 5, 6, 7. So which pathway do I choose? Because the difference between the two pathway are the substituents. Here's the rule of thumb. I choose the parent chain that gives me the most amount of substituents. The blue pathway here has two substituents. You got this group here and this group here. However, the red pathway, I have 1, 2, 3 substituents. Okay, so that red pathway is going to be my parent chain. And you might ask, well, why? I mean, it would seem better if I just made two substituents, it's a shorter name. I don't know, go back in time and ask the old guys that sat in that room in the IUPAC convention and ask them, like why did they do that? I honestly don't know. Um, so what I'm going to do is I'm going to kind of clear all this off here, and then I'm just going to highlight my parent chain. This is going to be my parent chain because it has 3 substituents. Now, if you look at this, I can number this a couple different ways, or I could start, I should say, in a different spot. I could do this 1, 2, or here 1, 2. Because the substituent encountered first both gets number 2. So what do I do? Well, then I have a third substituent. I want to make sure I give that one the lowest number. So if I were to go that way, it gives that ethyl group over here number 3. So that's the direction I'm going to number. Okay, so there's my numbering scheme for this parent chain. Now I'm going to name all my substituents. So on 2, I have chloro. On 3, there's an ethyl because it's 2 carbons, so prefix of eth. And then on 6, there's a methyl group. All right. Now I'm going to put them in alphabetical order. It might work out that it's also numerical, but it doesn't, that's not what we shoot for. All we do is we alphabetize them, and the way the numbers fall, that's how they fall. So with chloro comes first in the name because it's higher in the alphabet. So 2 chloro. Then ethyl comes next in the alphabet. So 3 ethyl, and then methyl at the end. 6 methyl. Now it just so happens that they're alphabetical and numerical, but we don't care about making them numerically in order. What matters is that they're alphabetized in the name. And it just so happens that they also are in numerical order. And then I put the parent chain. The parent chain has 7 carbons, so we call that heptane. All right, now what I would like you to do, I'm going to kind of stop the lecture here, is review these rules and try the problems that are on the next page. I'm going to make a separate video just for these practice problems. And then we're going to look at a couple more special cases that pop up with nomenclature. So as I said, I'm going to stop here and then I will make another video. You'll see another video with these practice problems.